All right, welcome. We are going to be running through several topics. I've already worked out the math and I'm just going to show you what's going on. So feel free to stop the video as we go. So we've got 5 topics we're going to run through. First is converting between atoms, molecules, moles, grams of the same compound molecule. So keeping the same molecule, but converting between those 3 things. Secondly, converting between moles and grams of either reactants, so converting from one reactant to the other, or products from reactants over to the products. Balancing chemical equations, including states of matter. Notice that the states of matter typically don't matter for balancing the equation. Determining the limiting reactant and reactants in excess, so either determining which reactant is limiting or which reactant is in excess. If one's in excess, how much is it in excess? And then calculating percent yield. Okay, so first, a few reminders. The mole unit is a counting unit. Other examples of counting units would be a pair, 2 things, a dozen, 12 things, a gross, 144 things. Those are all a number of things. It makes it easier for us to count things. So in this case, a mole is 6.022 times 10 to the 23rd of whatever those things are. The definition of a mole is that 12 grams of carbon-12, okay, so notice that's carbon-12, is 1 mole of carbon-12, okay? So remember, that's the isotopic notation of carbon-12. It's just a 12 with a C by it. When converting units with moles, you always multiply by the unit you're going into, divide by the unit you're getting rid of. So that's just dimensional analysis from back in the day. All right, so an example. Calculate the mass in grams of 0.105 moles of sucrose. First thing I've done is I have calculated the molar mass of sucrose. I've done it like you would type it into the calculator, basically. So you're welcome to do it like that. I'll show you in some of the work I show a slightly different method that's easier to do by hand. Then you convert from moles to grams. Okay. So you would take the value you're given, you multiply by grams, divide by moles. Notice that the moles cancel, and you're just left with grams. Okay, the result is 35.9, because even though you've got 6 significant figures in your molar mass, you only have 3 significant figures in your given value. All right, so calculate the moles of zinc nitrate in 143.50 grams of zinc nitrate. Notice that I have listed the numbers of how many zincs. There's 1 zinc. There's 2 nitrogens. There's 1 nitrogen in each nitrate. There are 2 nitrates. There are 3 oxygens in each nitrate. There's 2 nitrates. So 3 times 2, 6. Then you list their atomic masses, multiply, and you get those values. Add them up, and you get 189.39, accounting for the significant figures. Next, you take your given value, 143.50 grams. Notice that has 5 significant figures. And then you multiply by moles, unit you're going into, and you divide by grams. The grams cancel, and you're left with moles. Notice this has 5 significant figures, so 0.75770 moles of zinc nitrate. All right, so next let's talk about converting from between number of atoms versus grams. So calculate the number of chlorine atoms in 65.1 grams of magnesium chloride. First, calculate the molar mass. So I did that. Next, convert to moles of magnesium chloride. Remember, always divide by what you're getting rid of, grams, multiply by what you want. So moles of magnesium chloride. Next, you need to multiply by the number of chlorine atoms in magnesium chloride. So in every mole of magnesium chloride, there are 2 moles of chlorine times 6.022 times 10 to the 23rd, because every mole of magnesium chloride has 2 moles of chlorine. You multiply those 3 numbers together, you get 8.24 times 10 to the 23rd atoms of chlorine. Okay, the next one I haven't worked out in detail because I want you to work it out, but I do show you some tips. What is the mass in grams of that 7.7 times 10 to the 20th moles of caffeine, molecules of caffeine? Notice that 10 to the 23rd is 1,000 times bigger. So that means that you're going to have 1,000th of a mole of caffeine. Now, the molar mass of caffeine is around 200. So things 8 times 12, that's about 100, plus 10, that's another 10. 10 times 4 times 14, that's 56, and then 16 times 2, that's 32. You'll get around 200. I would say between 180 and 220. And then if you multiply those 2 numbers together, you get how many grams? And that's around 0.2 grams. Okay. All right, so next you've got balancing chemical equations. You've probably done this before. Okay. But first, just count the number of atoms or ions on either side, the reactants and the products. Okay. So in blue, I've done that. At the very beginning, when it's unbalanced, you will have 1 carbon, 3 oxygens, 1 carbon, 2 oxygens. But the next thing you would do is you would say, oh, I need to increase the number of oxygens on the right-hand side so that I can then get the left-hand side into balance. Because you only want to put in whole numbers here if you can possibly do so. They always need to be whole numbers at the end. So I would put a 2 on the right-hand side there. I've done that in blue. And that then update these numbers, get a 2 and a 4. And then that would cause me to update that number. So in green, I've done that. So there's 2 carbons now, and 2 plus 2, 4 oxygens in total. Now these numbers match up, and it's good. Okay, so here I've not worked this out in detail, but I'm pointing you to some things that would help you out. First, notice that you've got magnesium, nitrogen, hydrogen, OH. H2O can always be broken up into H and OH. And then on the right-hand side, I've got nitrogen again, and hydrogen. Okay, so those match. Magnesium, good. OH and OH. So everything matches. So sure, you could just list magnesium, nitrogen, hydrogen, oxygen on both sides, and you would be fine. Or you could list Mg, N, H, OH, and balance those. You'd be fine. Again, for B, I've underlined the ions. Sodium, chlorine, lead, nitrate. Lead, chloride, sodium, nitrate. And then this one is a typical kind of combustion reaction. It's a combustion of ribose. It's a 5-carbon sugar. And for these, you're always going to want to balance the CO2 and water first, then balance the oxygen. Then, if this number is a half, multiply everything by 2. Because you always need to have whole numbers when you're done. Okay, so let's talk about the example in the back of the paper. The chemical formula for glucose, by the way, is C6H12O6. Okay, so 38.4 grams of glucose is burned with 120.4 grams of oxygen. How much water would be produced theoretically, and how much is produced if 10.1 grams is actually produced. What's the percent yield? First, I just note the things what I'm given, what I'm being asked for. You always want to make sure you have that information easily at hand, and you want to make sure you actually answer the question that's asked. Okay, so first we need to balance our equation. So glucose plus oxygen yields water and CO2. Okay, so when you're done, you should end up with something like this. But remember, anytime you react something with a hydrocarbon or sugar with oxygen, you're always going to get CO2 and water. If you add in sulfur or nitrogen, you'll get things that look like SO2, SO3, NO2, NO3, NO, SO2, that kind of thing. But anyways, so you've got these, balance the hydrogen carbon first, then the oxygen, and you'll get that answer. Then I calculate molar masses, molar mass of glucose, molar mass of oxygen, molar mass of water. Lastly, here's our new piece. So we start off with what we're given, 38.4 grams of glucose. We want to convert from grams to moles. So we go grams, divide by grams. This is the molar mass of glucose, 180.156 grams of glucose. Moles of glucose go on top. Then we need to multiply by the stoichiometric ratio. So to get this, we look back at our balanced equation. It has to be balanced. And we say, for every 1 mole of glucose, we produce 6 moles of water. So I can multiply 6 moles of water divided by 1 mole of glucose. We then, in our calculators, type 38.4 divided by 180.156 times 6, we get 1.28 moles of water. All right. Now we do the same thing, but for the other reactant, oxygen. 120.4 grams of oxygen, that's what we're given in the problem. Divide by the molar mass of oxygen, 31.998. Multiply by 6 moles of water, divide by 6 moles of oxygen, and that's equal to 3.76 moles of water. Now, we're being asked to find out how much water is actually produced. So we need to figure out which one of these is based upon the limiting reactant. Well, 1.28 is smaller, and that means that it's the one that is limiting the reaction. So 1.28, that's our actual result. We could only get 3.676 moles of water if we had lots and lots of glucose around. Okay, so we start off with 1.28 moles of water here, convert that into grams, and that is our answer for the theoretical yield. Okay, but the actual yield, it said, was 10.1. So we take 10.1, we divide by 23.1, multiply by 100, tag on that percentage sign, and we get 43.7%. All right, so I'm going to give you some tips on the exercise, but I'm going to leave it to y'all to actually work through. So it does give you an equation, but it's not balanced. So the first thing you would want to do is balance that equation. And then it says, in experiment, 3.12 grams of ammonia, that's NH3. So NH3 is our ammonia, reacts with 4.21 grams of oxygen. Okay, so the A, balance the equation. B, which is the limiting reactant? There's 2 ways you can work these limiting reactant problems. You can convert them into a product, like and see which one produces the least amount of product. Okay, and that would be fine. That would help you answer question D. The other approach is to convert to the other reactant. So you take the ammonia and convert into oxygen. And you see, do we have enough oxygen to actually react with all of the ammonia? If we have enough oxygen, then the ammonia is not limiting. That implies O2 is limiting. So there's not enough ammonia to react with all of the oxygen. And then once you've figured out which one is in excess, you subtract the how much reactant would actually be used away from how much reactant you have, and that's how much is left over. All right, and then part E, if 3.51 grams is actually formed, then what is the percent yield? You would find out how much NO is formed, and then calculate the percent yield, just like you did for the example. So the theoretical yield divided by, the actual yield, the experimental yield, divided by the theoretical yield, multiply by 100%, and you get the value. All right, that's it. So thank you for listening, and I'll see you next time.